Hi, everybody. Welcome back to Artificial Intelligence. So as you hear, I catch the cold, so my voice is a little bit bad today, but I hope it's still okay for you. So last Friday, just after the Christmas break, we started talking about preferences for making rational decisions. And one thing that was important is that we have to fulfill certain axioms of utility theory. Because if you don't meet these constraints, we are not going to act in a rational way. So we discussed these points already: orderability, transitivity, continuity, substitutability, monotonicity, and decomposability. And as an example, I'm going to show you now that, for instance, if you do not respect the constraint of transitivity, that you will act potentially irrationally. And any other violation can also lead to irrational behavior. So the only way to ensure irrational behavior is that all these constraints are always met. So we look at a very simple example. Let's say you prefer B over C, and because of that fact, you would pay, let's say, 1 cent to get B over C. But also, so we have already this preference. So you prefer B over C, but also you prefer A over B, which is this arrow here. And again, you would pay 1 cent to get A instead of B. And now comes the problem. Then if you prefer B over C and A over B, then certainly you have to prefer A over C as stated according to this transitivity condition. But let's assume for some reason you prefer C over A and would again pay 1 cent to obtain C. Then of course you see that this is a spending cycle where you would lose potentially all your money because you always buy the next thing and you don't even improve because you're circling here. So this maybe, but this is, I don't want to get any shitstorm. A little bit is like looking at fashion cycles. So if you look at what people like to wear a few years ago, then this sometimes repeats, right? So I'm not an expert on this, but this shows that some fashion cycles might be irrational in the sense that you spend money, but in the end, you still have you don't have you could have kept the clothes and then wore them 10 years again. But again, of course, this example is not perfectly correct because some people feel very, very happy just by buying things. So then you can say that the utility is still improving and increasing, but in some respect, it would be some irrational behavior. Okay, good. So now that we know how to act rationally, and we already started talking about preferences, we now can talk about the fact that preferences lead to utilities. So if you know, of course, that you prefer A over B, then the utility of A should be higher than the utility of B. And if you're indifferent about A and B, then of course the utility of A and B should be equal. And of course, also what you can derive from these axioms of preferences is that there always exists an expected utility of a lottery. So if you're playing a lottery, and again, P were the probabilities of the outcomes of the lottery, and U were the utilities of the different outcomes, then the utility of this lottery is just the weighted sum of these utilities of the single outcomes. And utilities are not fixed. So you still have the same preferences. For instance, if for all the states S, you're scaling the utilities in a linear way, so you can multiply all the utilities by a factor A and offsetting them by a value B. And then, of course, the relative difference is what was before had a high. So every state that before had a higher utility value now also has a higher utility value, although the value itself has changed. So that's why there is no unique utility value. But this also doesn't matter because we just need the relative values. And one more note, so if you look into the literature, then they're often also used, you often also see the terms value function or ordinal utility function instead of utility function. There's a little bit of a mess, so there's not a clear term for that. And you sometimes have to just, keep in mind that the terminology changes depending on the community. Okay. Good. So now we have a few tweetback questions. So the first one is a little bit personal. Do you know what Russian roulette is? So it's basically you have a revolver. Typically, maybe a revolver has 6 slots for bullets, and you just put one bullet in these slots, and you point the revolver to yourself, or somebody else does this. And if you're lucky, nothing happens. If you're unlucky, you're dead. And let's assume you have a 1 million barreled revolver. So there's 1 million slots with just one bullet. How much would you pay to not play this game? So now there's different prices, like different amounts of money you should invest, starting from 10 euros up to more than 1 million. And then, it would be great if you could just show your preference. And of course, it's anonymous. Sorry. It's like at the beginning of the semester where I was sick. So usually I'm not sick one time during the semester, but this year is not good in terms of getting a cold. So do you already have some results?
Yep. So about 40% of people chooses A, and then about 20% chooses G, and the rest are more or less evenly distributed.
Okay. So the conclusion is that during the pandemic, life is valued less than when there's no pandemic. So we often had many A's and many G's, but not as many A's as this year. But okay, so it's your personal preference. So let's talk about this result later on. Let's just continue. So another example where money was put on the life of people, in particular students at a school. This example from the US. So this is taken from the AI book. So Ross Schechter had this very bad experience with a government agency which wanted to renovate the school building because it had asbestos. By the way, does anybody know why the previous computer science building is no longer existent? And who knows where it was before we moved into the current building? This is of course not an AI question, but maybe somebody knows. Yes, it was across the street from the Mensa from the downtown Mensa. So now there is the University of Film and Art, and below in the basement there is this Egyptian museum. So this was the area where the computer science department was located. And if I'm asking you already this way, it had asbestos. That's why it's not longer existent. So you as students were valuable enough to renovate the building. So anyways, so this school here needed to make a decision whether to remove the asbestos or not. So they decided to put a value on the life of each student. And then they argued in the report that the most economical way would be to remove the asbestos. And this caused quite an outrage. So the agency was morally outraged, and the idea of setting value to life was rejected. And of course, the asbestos was not removed. So in essence, they even put a lower amount of money for the life of the students. And this, of course, is even worse than the previous report. And actually, in reality, I don't know, has anybody of you worked for an insurance company before as a student, or maybe for real before studying? I don't know, maybe you don't have to say which company. Okay, so not too many people, obviously. And so insurance companies do that all the time. Also, like airline companies, whether they want to invest in new technology, they also put they also have a price tag for human life, essentially. And one common currency is this micromort. This is the 1 in a million chance of dying. And this is exactly, one micromort was exactly this 1 million barrel Russian roulette game. And people would typically pay huge amounts, so typically more than 10,000 euros to avoid playing Russian roulette with a 1 million barrel revolver. So this is according to a more representative survey. I don't know, maybe this survey is also outdated, but at that time, people would have paid more money. But if you compare this with decisions in daily life, then there's a huge mismatch. So for instance, driving a car for around about 370 kilometers is 1 micromort. Traveling by train is roughly 50 times safer, or by plane. So car travel is not that safe. That's why we're working, for instance, on autonomous driving. And if you look at the lifetime of a car, then this corresponds to 400 micromorts. And as I said before, people would pay 10,000 euros for 1 micromort. But if you ask them, okay, how much more money would you pay if your car is twice as safe? Then people would pay 10,000 euros roughly. And that only corresponds to 50 euros per micromort. So much more in the direction what you suggested for not playing Russian roulette. So we could also say that you're more rational because you know that micromort isn't worth that much, actually. Okay. Good. So let's leave this behind. But I also know that many of you just choose A just to be a little bit provocative. So it's not a statistically correct survey, usually what we're doing here. Good. So now let's go to the next feedback question. It's again about money. Today is a lot about money. So let's say you're a participant in a game show, and the game show master offers you to win 1 million euros straight away so you get the money for sure, or he will flip or she will flip a coin, and you can potentially win 2.5 million euros. So what would you choose, A or B? So please select.
Okay, so around 75% chooses A.
Okay, yeah, that's a good choice. I would do that myself, actually. So now we could discuss whether this is a good decision, or whether, I mean, good decision often means rational decision. And if you look at the expected value, of course, the expected value of B would be 1.25 million euros, which is higher than 1 million euros. So you could say in average, you could get more money by selecting B. However, and now I would like to switch to my whiteboard. So just a second, I forget to bring this up before the lecture. Okay. Let's talk about utility of money. So why does 1 second? Oh, I guess we have a small issue here. Maybe I start something new. Oh, okay. I had this bug before. As I said, usually I don't like to use Windows operating system because it has a lot of bugs. But because of this pad that I use, which has not such a good support in Ubuntu, I often have to use Windows, and I had to rearrange the my screens, and now my pen doesn't work anymore on the whiteboard. So let's move this away, and I try to do it differently. Wait a second. So we can just use again this annotation, and instead of using, does the pen work here? Again, no, because if I use the pen, it manipulates the screen I'm looking at where the camera is. Sorry for that, but it's not a big deal. So here would be the utility axis, U, and this would be the money axis. You can use this euro symbol, or you can use a dollar symbol, whatever. So typically, let's say you start at €0. The more money you have, the happier you are. And this is, sorry, this is a rather straight line at the beginning. But then at some point, you're like, okay, I have €1 million. If I have €2 million, it's not bad, but it doesn't make me much more happy. So this is kind of a flattening curve. So if you look at the extreme case, like some of the billionaires now investing in the space program, like Jeff Bezos built this gigantic penis for, like, I don't know, a huge amount of money and flew into space, then maybe it made him a little bit happier. So maybe he went from this happiness level to this happiness level, but the amount of money that he needed is, I'm just indicating this was a lot. So this is not a linear curve. Similarly, if you have debt, so the more debt you have, the worse it is. But at some point, you have so much debt that you will never ever be able to pay it back in your lifetime, and then you also don't care anymore about it. And then this curve is also flattening. Okay, so let's close this. Okay, we can go back to full screen. And now all of a sudden, this makes a lot of sense. So this is what we discussed. So the expected value is higher if you choose the second option, but sorry. But the utility, as I said, flattens. And let's say the utility, if you get 1 million euro, is increasing from 5 to 8. And if you get 2.5 million euros, would increase from 5 to 9. And now if you compute the expected value, sorry, for flipping the coin, then it's 0.5 times 5 plus 0.5 times 9. So this would be 2.5 plus 4.5. This is 7, and 7 is less than 8. So then the rational choice is to decline and just take the 1 million euros. So this would be the rational decision. Also, what I have to say is that everybody has the also this utility curve with respect to money is different for different people. So those who want to get the 2.5 million, they probably get even happier, or the curve stays longer in a rather straight upward trajectory. For those who say, okay, I'm good enough with 1 million euro. So this is a personal curve, and that's why also everybody essentially was right in the last survey. It's just personal preference. But what we learned from this is that money, using money directly, although we do a lot of things with money, money itself is not usually a utility. There might be some special cases where this is true, but in general, this doesn't hold. Okay. So far we had very simple discussions because we only looked at one attribute. But in many decisions, you have several attributes. Like if you want to decide where to place the next airport. So talking about former times, like I talked about this old computer science building, of course, also the airport wasn't always where the airport was in Munich. So before it was in Riem, basically close at the outskirts of the city. So the noise level, of course, for people in Munich was not that good. Cost in terms of building infrastructure to reach the airport was good. And death, yeah, I mean, it's not that relevant. There are some airports which are located in the middle of the mountains or close, I don't know. I mean, there are these crazy airports that you can look up also on YouTube. So there the location really has an influence on death. But whether the airport is in Riem or in like in Erdinger Moos, this is not a huge effect. Maybe a little bit better in Erdinger Moos because if a plane crashes, the chance that it hits a person is less likely there. I have to say, for me as a child, it was not good because I grew up close to the airport where it is now. But of course, for most of the inhabitants of Munich, this was a good choice. And of course, it's hard to say, okay, this one location has less deaths, but more noise. So what do you prefer, right? So it's like a little bit comparing apples with oranges. So this makes computing utilities much harder. Okay, so we need two strategies. And so, well, we don't need, but there are two strategies. One is that there might be some dominance solutions so that they're better in every respect. And the other thing is that there might be some independencies, like we looked at conditional independencies in Bayesian networks. And based on these conditional independencies, we might be able to assemble a utility for all these attributes based on utilities for single attributes. Okay, so this, the first idea was this dominance idea. This is the easy case. However, this usually does not occur in practice. If it occurs, yeah, you're lucky and you can sorry, quickly solve the problem. And in most cases, you have to make use of this preference structure. Good, so let's talk first about dominance, the easy case. So as I said, dominance means that one solution is better compared to the other in every respect. And we assume now that higher values means better utility. If that's not the case, you can just multiply the attributes with -1. So you see here, B is better compared to A with respect to x1 and x2. And so B dominates A. So this is a clear choice. However, D is better with respect to x1, but worse with respect to x2. So there's no dominance. And the same holds for C, which is better in terms of x2, but not better in terms of x1. So here you already see that these cases where one solution is best in all respects is rather rare. And it's even rarer if you look at uncertain values. So here we assume that the values are certain. So these red dots here, it could be that the utilities are uncertain within a certain set. And then, of course, for all possible values of B, they have to be better with respect to x1 and x2, considering all possible values of A. And this is the case here for B compared to A, but C again, B doesn't dominate C because C is better with respect to x1 in many cases, not in, maybe even in all cases. This is a close call. Okay. Good. So a type of dominance that occurs more often in practice, or rather often actually, is stochastic dominance. So what does it mean? So we're using now here negative values because then this makes the definitions a little bit easier. So meaning that a more negative value is better here. And this, the other lines show the probability distribution. So this is this first probability distribution shows the distribution of probability of a certain of the utility of a certain choice, and this solid line shows the distribution of another choice. And now what we do is we look at the cumulative distribution. So we integrate these probability distributions, and we of course see that the dashed solution is always greater than the solid solution. And in this case, we say that distribution P1 stochastically dominates distribution P2 because for each value that I choose, like here -4 or -3.5, the probability of the cumulative probability of one distribution is greater than the cumulative distribution of the other choice. Good. So what does it mean? So for instance, if you want to know to obtain the utility of 4, again, I multiply this with -4 because of this negative costs here. This probability is less if I choose S1 compared to S2. And for other utilities, that's also the same. Okay, and of course, it's not a given cost, but of course it is that at least the utility is 3.5, or at least the utility is 4. So that I should have said. Okay, good. So now additionally, if the utility is monotonic, so greater values of x means greater utility, which is typically the case. So otherwise, it's not really a utility. So that's so it would be strange if you say, as an example, if I have 1 million euros, I'm happy with the value of 10. If I have 1.1 million euros, I'm happy with the value of I don't know, 11, and I'm very unhappy if I have 1.05 million euros. So this would be irrational, and that's why the utilities are always monotonic. Good. So then, of course, because it's monotonic, then of course it means that because the probabilities are stochastically dominating, then it also means that the expected utility is always greater if one solution is stochastically dominating the other solution. Sometimes you don't even need this exact probability distribution. You can just use common sense. So for instance, the cost of the airport increases with the distance from the city. because the argumentation is that you need that the transportation to the airport, that the transportation infrastructure you have to build for the airport is more costly. Let's say if you build a train from the city center to the airport, then this is more costly the further the airport is away from the city. But of course, the costs themselves are uncertain because there might be a swamp that you forgot or whatever, or the price of steel has increased or decreased. And so there is uncertainty in the cost itself. But the closer the airport is, the more likely it is that it meets the given budget limit. So that means that the stochastic inequality here holds. And if that holds, then we have stochastic dominance. So you can also think of it like, okay, what is the probability that the cost is is not greater than a certain amount, then the probability would always be lower, and then you directly basically have this cumulative. You directly argued that the cumulative distribution here is always greater than in one case than in the other case. Good, and now we can look at the a practical example. So this is again the same car insurance example that we discussed before. So if you look at vehicle year and airbag, is there some positive or negative correlation? So meaning that the larger or the higher the vehicle build year is, the higher is the probability that it has an airbag. Is that true? So that would be plus, so it's positively correlated, or minus, so that it would be negative. So you can just type it in the plus or minus in the, or zero if there's no correlation in the, yes, so this is positive. So that means the higher the vehicle year, the higher is the likelihood of an airbag. And so risk aversion and anti-theft. So if a person is very risk averse, then the likelihood that that person will install an anti-theft system in the vehicle is also positive. Anti-theft and theft is negative, because if you have an anti-theft device, the chance of theft is reduced. Then we have mileage and car value. The higher the mileage, the less car value. So this is negative. Age and medical costs. So the older you are, typically the higher are the medical costs. So this is positive and so on. There's just a few examples. We don't have this direct correlation. So the higher the risk aversion is, this has not really an influence on the make model, or like social economic circumstances have no influence on the make model and so on. So here we can say then of course that based on these correspondences, we can directly then see which are stochastically dominated, which variable pairs are stochastically dominating. Okay, so this is then the dominance. This was the dominance part. So either it directly dominates or it stochastically dominates. And now let's talk about preference structures. And as I said before, maybe we can find some independence relations, and based on these independence relations, we can assemble then the utility of all attributes given the utilities of single attributes. So let's again use the airport problem, and we define preference independence as follows. So two attributes x1 and x2 are preferentially independent of x3 if and only if preferences between x1, x2, x3 and x1 prime, x2 prime and x3 prime do not depend on x3. So if I change x1 and x2, then what value I have for x3 doesn't matter. So in a given example, or in the airport example, this would look like this. So the decision whether I prefer that 20,000 suffer from noise and that the costs are 4.6 million and I have X number of deaths compared to 70,000 suffer from noise, and the airport costs just 4.2 billion, sorry, and I have X number of deaths, then the choice doesn't matter on the value of X. Of course, X should be equal in both cases, but whether it's 10 or 100 or 1,000 wouldn't change my decision which of these two I would prefer. So then X noise and cost would be preferentially independent of safety. Okay. So now if every pair of attributes is preferentially independent, so in our case, if noise and cost is preferentially independent of safety, or noise and safety is preferentially independent of cost, and cost and safety is preferentially independent of noise, then this applies to any subset. So then you could also, this is not a good example because we just have 3 attributes, but let's say you have 5 attributes, then you can, for instance, choose if for each pair of these 5 attributes, you have this preferential independence, then that would also mean that if you just maybe choose 3, then these 3 attributes would also be preferentially independent of the other 2 remaining attributes. This is called mutual preference independence, was already discovered in 1947. And if that's the case, then you have this very simple additive value function. Sorry again. So that means that the value function of all attributes is just the summation of the value functions of the individual attributes. And often it is the case, even if you don't have perfect preferential independence, that this can be a good approximation. Okay, sorry. Good, one more thing, and then I start the break. Sorry, I have to cough now a little bit more because of all the talking. Okay. So unfortunately, it's not as easy that the previous results can be directly translated to lottery. So here we talked about prices directly. So we had a deterministic preference structure. And now we look at stochastic preference structure. So we want to have preferences over lotteries. And then we cannot have this additive value function. Again, we use independence. And we use something called utility independence. So a set of attributes X is utility independent of Y if and only if preferences over lotteries in X do not depend on attributes in Y. So it's similar, but now we're talking, as I said, about lotteries. And again, we can obtain this mutual utility independence. So if each subset is utility independent of its complement, then there exists this multiplicative utility function discovered in 1947 by Keeney, which is more complicated, of course, than this additive value function. So here, if you have the utility 1 of variable x1, and this is abbreviated as just u1 here, and the utility of attribute 2 and the utility of attribute 3, then of course you first sum these 3 utilities with factors k1 up to k3. And then what you still have to do is you have to look at all these pairs. So u1 and u2, u2 and u3, and u3 and u1, and you use the same k values, multiply them and add them all together. In the end, you have this last one, which shows all combinations. Of course, if you have 4
questions from Tweetback, if you could explain the difference between, I guess, deterministic and stochastic independence, a bit more careful.
Yes, I will do that. So just one more thing to just finish this. So if you have 4 attributes, then of course you don't only have all the possible 2 pairs, but all possible 3 pairs up to then the multiplication with all 4 values. But of course, to generalize this formula, which is possible, the mathematical formula for that would not be very beautiful, and it's easier to explain this by example. So this is just an example for the case with 3 attributes. Okay, so now again, the difference between stochastic and deterministic preference structures. Just to make sure, although we discussed this at the very beginning, just so that everybody's on the same page, I think everybody remembers, but what is the difference between a prize and a lottery? So if you have a prize, you get something for sure. And if you, in a lottery, you get something only with a certain probability. And in the first case, we just talked about prizes. Sorry. So I mean, whether an airport or not, whether an airport is a prize or not, as I said, prizes just means is the word that is used in utility theory for you get something for sure. So either you get this airport which where 20,000 suffer from noise and you have this amount of cost and this amount of death, or you get this. And in order to decide what is better, because we have this mutual preference independence here, meaning that if you decide between noise and costs, then this is independent of safety, because no matter what the safety level is, you would still make the same choice as long as the safety level is identical for both choices. So X is an arbitrary number, but it's always the same in both cases. So then if this holds for all combinations of attributes, then we have this mutual preference independence. So the difference now is that we're not talking about prizes, but about lotteries. So let's say if there are all these betting things for I don't know, for football or whatever, or for sports. I don't know what is typical, or there's different companies offering that. And you want to make a choice which lottery you want to play. So should I play this lottery or that lottery? And the lottery has several attributes. Then you cannot just take the individual attributes of the lottery and take those utilities and add them up. So what you then have to do is you have to use these more complicated utility values. And of course, the utility values themselves already contain the probabilities of the outcomes of the lottery, right? So that's why you don't see any probabilities here. So these U's are, yeah, where do we have it? Yes, so the U's are these U's of the lottery where we already factored in the probabilities of the outcomes. And because it's a lottery and not a prize, the mechanics of that changes, and you cannot just add up the utilities. I mean, the reason for that is rather complicated, and I know that we are cutting this short here in the lecture, but it should just be you should just remember that when you have preference structures between lotteries and preference structures between prizes, that you have to use different formulas. So you cannot just use the same mechanisms for lotteries than you use for prizes. So this is basically the take-home message here. And again, the derivation of this is also not in the AI book. I mean, you can look at the paper, but and we just use one slide for this whole topic. So this is like a whole theory, which is, and all this whole utility theory is also a major area in economics. Yeah, I mean, we cannot discover or we cannot present each topic in great detail. That's why we're cutting it quite a bit short here. But as I said, the take-home message is that if you have preferences between lotteries, then you have to use different formulas. So I don't know if it was a better explanation or if there's still
well, there are no more questions, so I guess you could continue.
Okay. Or maybe because we're at the middle of the lecture, and this is a good point, because now we started with a new kind of subtopic. Let's have our 5-minute break. I'll drink a little bit more tea, but my coughing will not be much better, I have to say, in the second half, but I think it's still okay. And so let's meet again at 5:07. Good. So let's continue with decision trees. The good thing about decision trees is they're super easy to understand, and so the next slides will be super easy. And this is a tool. If you have a very simple problem and if you want to make a rational decision, then this is the way forward. Okay, so a decision tree consists of 3 things. So the first are the decision nodes, which are rectangles. So this is where the decision is made. Then you have the diamonds, which are responsible for the utilities. And finally, you have ovals, which represent random variables, exactly as for Bayesian networks, where we used also ovals for random variables. So, and what is written here is that if you want to compute the expected utility of a decision, you just have to then sum over all the branches in a weighted way the utilities. And in the example I will show you now, it will become very apparent how this works. So let's say after you studied computer science, you became rather wealthy, and now you want to share this wealth. You have a lot of people of influence that you know, and you want to organize a garden party for fun, or you want to organize a fundraising garden party. And of course, you have always the risk that it rains and the people will not show up, and you will lose money for organizing the party, but not doing any fundraising for a good cause. If you won't do this party and it doesn't rain, then of course you can do something else fun, like playing sports or something, doing sports or playing games or whatever. And this is also has some utility, of course. And the probability of rain that day is rather high with 60%. And you have these utilities. So the first one is there is a party and it's raining, then it's -100 because you invested money for the catering, for instance, but nobody shows up. Then you have the party in the snow rain. Then that's a good utility of 500 because you're doing a lot of good, which makes you very happy. And then you have no party and it's raining. Okay, then you couldn't have done anything else, so that is the utility of 0. And if there's no party, it doesn't rain, as I said, you can do something else fun, which would have a utility of 50. So now if you look at this decision tree, even if you don't study computer science or have no clue about artificial intelligence, you can tell me whether you should let the party happen or not. So how would you compute that? I mean, it's basically just high school mathematics you need here. Or maybe somebody, can somebody write what is the utility in the chat if we choose to have the party? How do we compute the utility? Okay, good. So 500 times 0.4, yes. plus minus 100 times 0.6. That's correct. So you always use the probability multiplied with the utility, and then you add all, you add up all cases. And the same for no rain. So then it's for no rain, it's even easier. 0 times 0.6 plus 0.4 times 50. So 200, that would be 20. Okay, so let's look at these two cases, 140 and 20. And of course, then because the expected utility for party is higher, we choose to do the party. Because this example is so simple, we don't really need any formulas, but for those who prefer deriving this from a formula, we can use formula 6 from slide 7. Let me just briefly go back. So this was this formula here, where we said, okay, the expected utility of x is multiplying the utilities with the probabilities and summing over all values of y, which we've done here. And there you just need this to really use this formula. You just need this. Keep in mind. Wait a second. You just need to keep in mind that the probability of rain and party and rain and no party is the same as rain, since party is just a decision variable. So once you made the decision, there's no uncertainty left. So that's why you have not probability of rain, comma party. We already included the simplification here. Okay, so this is super easy. So let's say you have to make 2 consecutive decisions. So maybe the first decision is you want to have the party or not, and the second decision is you want to get drunk at the party or not. So then how many branches do you have if you have a second Boolean decision? I mean, instead of drunk, you can also make a decision whether you want to give a speech or whatever at this party. But sometimes you want to have more than, so then you already have then you already have 8 branches. And as you can see, the more decisions you have and the more stochastic variables you have, this the branching is exponential. So this whole approach only works for smaller examples. So here in this case, we just used a very small example because it fits on the slide. I mean, 2 decisions is still fine. But if we have 3 or 4 decisions, then we need something better. So as an extension to this, we will look into decision networks, which can be seen as Bayesian networks for decisions. But before we get there, we want to talk about the value of information. Okay, so this discussion we already had. So it's a very general method. It uses this explicit encoding of utilities and probabilities, so it's very transparent. It's especially helpful for small sequential decision processes, but this tree becomes exponentially complex with increasing number of sequential decisions. And that's why we will use decision networks later in this lecture. But before, as I said, we want to talk about the value of information. So before you make a decision, you also need some information. So for instance, for the garden party, we needed at least a probability whether it will rain or not. Okay, you can now go in the internet and check whether it will rain or not. So this is very little cost. At least there's some cost associated because maybe you need some time, or you can say, okay, I need an internet connection, and which costs me so and so much every month. So if I use it for 1 minute, then this has this cost. I mean, anyways, the cost is very low. But there are other problems. For instance, in medical problems, we're getting more information requires maybe that you go in, you get into an MRT scanner or something like that. Then this is associated with higher costs. And then the question is, how much should we pay for information, or should we just say, what the heck, I'm just making this decision without this additional information. Okay, so this is actually what I just told you essentially. So here's another medical example. A doctor has to carefully select the diagnostic tests and questions most important to the patient. So this is an important thing to do. And of course, information value theory guides then an agent to choose what information to acquire. All right. So let's start with an example. And we're using this oil drilling example from the book. And I mentioned before that I actually don't like these oil examples because we have a climate problem, we want to have a green economy and so on. So even from the 3rd to the 4th edition of the AI book, they haven't changed this example. And we usually kind of want to stay close to the book, because the advantage of that is that if somebody wants to read this again, you can read the example in the book, and maybe it's explained there differently, the way I explain it. And maybe sometimes I explain it better than the book, and maybe sometimes the book explains it better than I do. So it's good to stay close to the book. So that's why we're keeping this. Nevertheless, then I got emails or that saying, you should advertise things related, where AI is used for better, cleaner economy. And actually, we have projects on this. So we have 2 projects where we use AI for power systems, and especially for renewable energy systems, to make decisions when to maybe charge batteries, when we have a lot of energy in the grid, make predictions about what the weather will be like, try to estimate the behavior of consumers and so on, to make optimal decisions. But at the same time, and that's our specialty, we want to prove that the decisions that we make do not cause a blackout of the energy system. Because as you will see later on in lecture 13, when we look into machine learning techniques, a classical machine learning technique doesn't have any guarantees. And if you have a technical system, then often you have safety or operational guarantees to fulfill, and then you cannot use a standard machine learning algorithm. And so we have a research project on that. And at the end of the semester, Michael and Hannah, who will work on this project, will also present you some possible topics for thesis or for seminars and so on, if you want to contribute to a greener economy. Okay, so much as an introduction. So the problem is, and I would like to show this to you with my pen, but as I said to you, there is this bug. I had this before. It doesn't occur a lot. That when you change the configuration of the screens, and I use my tablet here, so you can see this thing here, then it, for some reason, works on the wrong screen. So I have to use my computer mouse. So I will not be able to, I wanted to first derive all the equations, but now I will just show you some basic sketch of the problem, because this I can still do with my mouse. So you basically have several squares, and you can buy each square, or you can buy the drilling rights of a square. It was like this. And you have n squares, and only one of them is oil. So I don't know, maybe this one is oil, and the other one doesn't have, the other ones don't have any oil. And buying drilling rights has cost of C divided by N. N is the number of regions that you can buy. And the value of the oil in one of these squares is C. And now you want to know whether it's worth to ask a seismologist, or how much you should pay a seismologist so that the value of information that you get is higher than the cost for obtaining this this information. Okay. So let's continue with the full screen. So that's what I said. One block contains oil worth C euros, and the asking price for each block is C divided by N. And a seismologist can tell if oil is in block 3 and how much should the company pay for this service. So maybe I still try to explain it step by step using my mouse, but it will not be particularly pretty. So let me just get the numbers up again. Oh yeah, okay. Okay. So let's say you first want to know what is the average profit I make if I don't use a seismologist. So if you're lucky, with probability 1/n, you hit oil, and if you hit oil, then you make a certain amount of profit. So this is C, is the amount of money you get from the oil, but you have to subtract the cost for the drilling rights, which is C/n. And wait a second. Why? Yeah. So in the slides, I did it a little differently. So so the cost or the profit you make is then n-1. So it's just a rewriting times C/n. Okay, and if you're unlucky, of course, sorry. Okay, so this is already the case. Sorry, I got confused. So this is already the case that we're hiring the seismologist. So you can say, of course, on average, if I don't use the seismologist, you can see this directly. What is the expected profit that you make in this case? So somebody wrote 1/n times C. So that's the expected value you get. So you have a 1/n chance that you get the oil worth C, but then you always have to subtract the cost for the drilling rights, which is also C/n. So on average, if you don't use a seismologist, on average, you make no money. So this is not a really good deal. So now we are hiring the seismologist, and he can tell us whether there's oil in block 3 or not. So this is the first case is, there is oil in block 3, and the probability of that is 1/n, and the profit is C minus C/n. That's the first case. And the second case is the seismologist says there's no oil in block 3, but then the chance of finding oil in the remaining blocks because of this information has increased. So it used to be 1/n, but now it's 1/n minus 1 because we could exclude this block 3. Sorry, And then, of course, we have sorry, I'm really sorry about that. So we have with probability of n minus 1 over n, we still have the survey says there's no oil. No, it was all it was all correct. So I'm sorry. Because of, maybe it's also because I'm a little sick that my focus isn't there today. So it's 1 over n minus 1 is the chance that we find oil in one of the remaining regions, and the profit we can make is it's with this chance we get C amount of money, and then we have to remove C over n for the costs of the drilling rights. And if you are rearranging this, then you get C over n times n minus 1. Okay. Good. So now we have to consider the probabilities of these two possible events. Let's change the color. So the first event, as I said, has a probability of 1 over n, and the second event has a probability of n minus 1 over n. And then you have to multiply these probabilities with the expected utilities. So this is expected utility for this case, and that's the expected utility for the other case. And then you know how much your profit has improved given the information that whether there's oil in block 3 or not. So I'm really sorry for this, for the confusion I created today. So let's stop this here. Okay. Okay, so this is again with probability 1 over n, the survey indicates oil in block 3, and the company buys the block and makes profit of C minus C over n, which is this value. Oh, okay. For some reason this, yeah, okay. So then with probability n minus 1 over n, the survey says that there's no oil, and buying another block increases the chance to 1 over n minus 1, so that the expected profit is now C over n minus 1 minus the cost for the drilling rights. And so this is then the expected profit for this case. And now for these two cases, we have to weigh them with the probability that there is oil or there's no oil. And then we obtain C over n. And that's the maximum amount that you should pay the seismologist to get that information. Because if you would pay more, then you would lose money. So as we've seen in the simple example, the expected value of information is the expected value of the best action given the information without any charge. So it's like if the seismologist works for you without being paid, minus the expected value of the best action without the information. So in this case, without the information of the seismologist. So basically, the phrase value of information now refers to this value of evidence of these random variables AJ, which have not yet been revealed. So that means that we discover the value that we now know what the exact value of this random variable is. And this can be written in a more mathematical fashion. So without this additional evidence, we have this maximum expected utility here. So we choose the action A that maximizes the expected utility, of course. And this formula we've used several times before. This is nothing new. Again, we multiply the probabilities of the outcomes with the utilities of the outcome. And the only difference is now that when we additionally have the additional evidence EJ, then of course we have new probabilities which are sharper, which are better because we know more. And because we know more, we can make decisions which can better maximize the expected utility. And it's always the case that additional information provides better results, because in the worst case, you can just ignore this information. So that's very obvious. Okay, the only thing that we haven't considered in this formula is that we don't know which value the random variable EJ will have. So if it's again a binary problem, it could be on or off. We don't know which one, and or it could be one or zero or whatever. And so what we have to do is we have to consider both cases and weigh the maximum expected utility for both cases with the probability that it will be one outcome or the other. So this is done here. So here we have this maximum expected utility from the previous slide. So this formula. But of course, we have to consider that the evidence that will be revealed, so whether there is oil or there's no oil, that this is uncertain. So we have to go through all possibilities. So in this case, with the oil drilling, there's just 2 possibilities. And then we multiply this with the probability of these 2 possibilities. So this then tells us what is the maximum expected utility if we get this additional information and we don't have to pay anything for it. And then we subtract the maximum expected utility without having this additional information, which is exactly according to the basic idea that we formulated. So this is then the formula. And here I showed you how to compute the value of information, in a direct way, because this is a very simple example. But of course, we can also use this formula now. So essentially now in the next slides, I show you how this formula can be used in practice. For this very simple example, however, this is much more compact. So because the formula is very general and works for arbitrarily complicated examples and can also be implemented in a computer program and so on. So there is definitely a use for that. But for a very simple example like this one, some people might say, oh, why don't you just compute it this way? But as I said, it's a general formula and you can automate this using computer programs. But here we calculate this by hand so you get a better understanding of how this formula works. So the first thing is we compute this maximum expected utility without this additional evidence. So this is basically this part. And the formula, of course, is exactly this formula. So we have to find the best action. And in the oil drilling example, because we have no information which from the seismologist, it's just guessing. So any action is as good as the other action because we assume that the probability where oil can be found is equally distributed. So without loss of generality, we then choose to drill in region 1. So A with index I means that we buy the rights of block I. So here we choose 1. It could have been any other one. This is without loss of generality. And then we just have to multiply the probability that we find oil in area 1 multiplied with the utility of oil plus the result that there's no oil in area 1 with the utility of no oil. Of course, if there's no oil, the utility is just the cost. And if there's oil, it's C minus C over N. And we see that as we have already reasoned without this formula before, that on average, if we don't have any additional information, we make no money at all. So the maximum expected utility without any additional information is just 0. Okay, now let's bring in the seismologist, and he can or she can tell you whether there's oil in block 3 or not. And the seismologist either says, yes, there is oil, or there's no oil. So E1 is one outcome and E2 is the other outcome, right? So these were the possible outcomes that we considered here in the formula. Okay. So when there's oil in block 3, of course, we choose block 3. So the best action is to drill in block 3. And then we get the utility of the oil. And we would never, ever not drill there, because if the seismologist says there is oil, then there is oil. Good. Yes, so it's just probability of 1 because we know there's oil multiplied with the profit, which is C minus the cost, C, which is C over N. And then the other case is there's no oil in block 3, but we know for sure there's no oil. So then we choose any other block. Here we again choose block 1 without loss of generality. And again, we have now to use this other probability. Instead of 1 over n, we have 1 over n minus 1 because we can exclude block 3. And the profit is, as always, C minus C over n. And the probability that there's no oil is n minus 2 over n minus 1 multiplied with minus C over n, which is just the cost for no oil. Okay. Good. And now we have to assemble everything together. So we use the general formula. This is 0. We computed that already. Now the probability that the seismologist says that there's oil is 1 over n multiplied with the maximum expected utility, which we have obtained here, C minus C over n, plus the probability that there is no oil multiplied with the maximum expected utility given that additional information, which is this rather complicated formula. But after some simplifications, we obtain a value of C over n, which is exactly the same as we obtained previously. Okay. Good. Are there any questions regarding this formula?
There was a question in the Zoom chat. Is the A the same as the alpha in the formula?
That's a good point. So we used alpha here. So we used everywhere alpha, right? I mean, A is the action, and alpha is then so we cannot use a specific A because we want to choose the best A. So this is basically the alpha stands for the best action, and alpha with index E, which with another index J, means the best action given the evidence EJ. So that's what this means. So here it's also said the value of the current best action alpha. So alpha stands for the current best action, and A stands for in general for an action A. And I think then here the alpha, and in the subsequent formulas, the alpha should be used consistently. So here we have the alpha, but then this alpha is replaced with the max operator. And then by thinking about the problem, we replace the max operator with a specific action. Here A1, and here with A3, and in the other one it's A1 again. So I hope this clarifies this question. Okay, so one thing that I would like to discuss is how valuable a certain information is. You can often infer without exactly computing the value of information. And as an example, let's assume you want to go, I don't know, skiing in the Alps or whatever. And there are two different routes. So one is a highway to a low pass, which provides good utility because you get where you want to get very conveniently. So this is this first distribution here. And the second one is you take a winding dirt road over the top, and the utility varies because there could be avalanches. So because of heavy snowfall, an avalanche could block a road. And then, I mean, as I said, getting weather information is cheap, but let's assume you're in Canada and there is no weather information because the area is so remote that you have to request a specific satellite service for this. And in the case that you see here, the question is the value of information high or not? So you see that in many cases, not in all, so there's some overlap. The utility of the first choice is better than the utility of the second choice. But the question is, if I get additional information, would that for this problem setting be useful or not? So that's the tweetback questions. So yes would be it's worth a lot, the additional information, and no would be it's not worth a lot.
Okay, so about 60% chooses no.
Okay, yeah, that's the correct answer. And why is that correct? Because even if you get additional information, it's very unlikely that the second choice will be better. I mean, you see there's just this small overlap, and the overlap, so that U1 is less than U2, the probability is really slim. So no matter what the answer is, whether there's an avalanche on the route in U2 or U1, in 99.9 cases, it's anyways better to choose U1. So this information is rather worthless. So it's not a high value. So let's look at another example. So you have to now choose similar winding dirt roads. So the utilities are still, so they are similar now, not as in the previous case. One is slightly shorter and better. So U1 is still slightly better. This is this one. And U2 is slightly worse. And the question now is again the same with the satellite report. Would you pay much for this report or not so much? So again, are the satellite reports worth much? Yes for yes, and no for no.
Now about 85% chooses yes.
Yeah, that's also correct. Very good. So now the additional information makes a big difference, because it could very well be that there's an avalanche and that the utility U1 is less than utility U2. So basically with the report, we can assume that we now know essentially the exact value, or at least that the distribution has been significantly narrowed. And then we can make a choice that is clearly better than if we would not have this information. So here it's worth a lot. And now another case, again, we use similar winding dirt roads. However, the distribution of the utilities is much narrower. So you see, it's a rather narrow distribution compared to what we discussed initially. So again, what would you say about the value of the satellite reports?
Now about 75% chooses no.
Yes, that's also correct. Very good. So the thing is just that we have not much uncertainty here, right? So that means like, okay, if you have more certainty, maybe U2 and U1 will slightly change when you have exact value, but they change just within this narrow distribution. So you don't gain a lot utility. And then also the value is not that high as in this second case. So here the value was really high because the value could change a lot and make a big difference. And here the value wouldn't change a lot. So this is just some intuition where you could do some qualitative reasoning, how much value of information is worth, or what the value of information is for a certain problem. Yeah, so it deepens a little bit your understanding. That's why it's in the lecture. Before we stop, and we're a little bit in overtime already, just quickly a few properties of value of information. It's non-negative because, as I said, having information is always good. You could just throw it away. That's why it's, if you don't need it, that's why it's always positive, can never be negative. It's also non-additive. So you cannot take the value of information and add the value of information again, let's say for the same evidence. Because if somebody tells you there is no avalanche on this dirt road, and you take a second satellite report, then the second time you ask for the same report, it has no value anymore. So you cannot just add up these values. And the other one is order independence. So the value of information for EJ plus the value of information for EK, given that you already know EJ, is the same as first obtaining EK plus the value of information of EJ, given that you already have EK. So the order here doesn't matter because we're looking at a static problem. However, of course, if you have a dynamic system, as we will look at in the next lecture, then at what time you obtain the information, then it makes a difference. But here, if you now look at the static problems of this lecture, it doesn't matter. Okay, good. So then let's stop here. And tomorrow we just have an exercise, if I'm not mistaken. So then we see again next Thursday. So that's good because then I can recover in the meantime. And we just finished the decision networks, which is an extension of decision trees. So we will certainly finish that next lecture, and then we can already start with Markov decision processes and reason about processes that change over time. And that will be a very important building block for reinforcement learning, which we'll then discuss in lecture 13 as a machine learning algorithm. But in lecture 13, we will also discuss decision tree learning, which is a supervised learning mechanism. So that you also get an idea of machine learning techniques. But as I said, since we have a special lecture on machine learning by Stefan Günnemann, we are not going into too much detail there. Okay, good. And then also we will show you regarding reinforcement learning, we can also show you some results from our own research, which will be quite interesting. Okay, thanks for bearing with me, although I had this bad voice today.